All right, let's look at inductors in series and parallel. Inductors, just like resistors and capacitors, they can be placed either in series or parallel. If you're interested in increasing the level of an inductance, you can put a bunch of them connected in series, just like you did with the resistors. And if you put them in parallel, then it definitely decreases the inductance value. Exactly identical to what we did with the resistors. So if you got a bunch of them, let's say L1, L2, L3, and all the way to L sub n is connected in series, as shown in figure 48. Just simply L total to be L1 plus L2 plus L3 all the way to L sub n. If you put them in parallel, then 1 over L total would be equal to 1 over L1 plus 1 over L2 plus 1 over L3 and so forth. One special case, just like we do with resistors, if you got two inductors that are connected in parallel only, L1 and L2, or you could take them two at a time. There'll be a product over the sum, would be L1 times L2 divided by L1 plus L2. As an example, let's say you have 4 inductors, 3 of them connected in parallel. The combination of those 3 is connected in series with L1. And also we have a 1.2 kilo ohm resistor. You want to reduce it to the simplest form. So if I look at these 3, let's call those L prime total would be equal to 1 over L2 plus 1 over L3 plus 1 over L4. L2 and L3 identical, so that the combination of those two in parallel just simply give 0.6, so it'll be 1 over 0.6 plus 1 over 1.8. Now you have 2 of them, then it'd be a product over the sum, 0.6 times 1.8 divided by 0.6 plus 1.8. Calculate that, it gives you 0.45 Henry, and all of those 3 then is connected in series with L1, so it'd be 0.45 plus 0.56, it gives you 1.01 Henry. So L total is 1.01 Henry, then you add that to 1.2 kilo ohms connected in series. Steady state conditions, just like we did with inductance, with the capacitance, we also discuss the inductance at a steady state. If you ignore all the internal resistance and a straight capacitance, an ideal case of an inductance can be replaced by a short circuit equivalent once it reaches steady state conditions. This is only true for DC. When you have AC, we're not going to talk about it in this course, but we will discuss it if you do AC analysis course. The inductance, it does have what is called the reactance. The combination of a resistance and the reactance itself, it gives you what is called the impedance. The reactance of an inductance is a function of the frequency. It's also equal to omega times L, where omega is a radiant frequency, which is 2 pi f. So it does act against any frequency. So if you're looking at the 60 hertz, the power is coming out of the outlet, 2 pi times 60 is whatever that number comes out to be. You have to multiply by the inductance value. That product give you impedance, which is actually in ohms. So if you have at a DC, the frequency is 0, so therefore the reactance is equal to 0. Once you go through that steady state, the transient, that steady state, the reactance is equal to 0, so it acts like a short circuit. That's why we draw the equivalent circuit for the inductance for DC at a steady state, it acts like a short circuit. For the capacitance, it's 1 over omega times C. That's the reactance for the cap. It's exactly opposite. So the very low frequency, it acts like an open circuit. At a high frequency, it acts like a short circuit. And there's a lot of application use that, especially it's called capacitance coupling to block any DC. But recall that the term steady state implies that the voltage and the current level have reached their final resting values, final steady state conditions, and will no longer change unless there's a change, either applied voltage or circuit configuration or some kind of a new excitations or some kind of disturbances that you have. Other than that, at the steady state conditions, it's the conditions of DC when after 5 time constants. So either during the storage or release phase, either during the charging or discharging. As an example, let's say you have a 10 volt source that is hooked up to 2 ohm resistors and a 3 ohm resistors in parallel with 2 Henry. if you draw the equivalent circuit, you're going to treat this like a short circuit after the transient response. So at a steady state, you replace a short circuit here. And if you're interested in calculating the current I1, the current at a steady state to the inductance, well, that short circuit is automatically short circuit out this 3 ohm resistor. So if I look at the voltage across a 2 ohm resistor, this simply be equal to 10 volts because that point is now the same as the ground. So I got 5 amps is going to from the source going to R1, but none of them is going to go to that resistor. So the current I1 is just simply the same as the current I total is equal to 5 amps. Another circuit, let's say you have 2 inductances. If you draw the equivalent circuit at a steady state, this is short circuited, and this is also short circuited. So if I put a short circuit here, that would automatically short circuit this 5 ohm resistor. It's same as if you take it out of the circuit, there's no current flowing to it because all the current is going to go around to the inductor. So if you after the current I and the current I1, the current I just simply be equal to total resistance, 21 volts divided by the R total. And R total is just be simply these two connected in parallel. So it'll be 3 times 6 divided by 3 plus 6. That gives you 2 ohms. So the current I total will be 21 divided by 2 ohms. That gives you 10.5. So that's the total current coming in. It's just going to go around the loop like that. And for the current I1, I total, the current I1 is just going to be current I. It's going to split up between R2 and R3. Just use the current divider rule. The current I1 just simply be equal to 10.5 amps multiplied by 6 divided by 3 plus 6. That gives you 7 amps. As an example, it says find the current I of L. In this case, in this example, you have an inductance and capacitance in the circuit. You want to calculate the current to the inductance and the voltage across the capacitors, V sub C. Draw the equivalent steady state conditions. This is shorted and replace it with an open circuit. If I look at the current I of L, in this case, this is open circuit. All the currents from the source is going to go around that resistor to an inductor. So it'll be 10 divided by 2 plus 3. That gives you 10 divided by 5, which is equal to 2 amps. This is open circuit, so the current I here will be 0, so this voltage will be equal to 0. So the voltage across the capacitor, if I put a voltmeter here, it's going to measure the voltage directly across R2. Or you can use a voltage divider rule. So the V sub C then will be equal to total voltage multiplied by R2 divided by R1 plus R2. That gives you 6 volts, not 6 amps. It should be 6 volts, but or you could have taken R2, which is 3 ohms, multiplied by I of L. So 3 times 2 gives you 6 volts. That would have been the same thing to calculate the voltage V sub C. Another example is says find the current I1 and I2, and the voltage is V1 and V2, assuming the steady state condition has already been reached. So you draw the equivalent circuit. If there's an inductor, you replace with a short circuit. If it's a capacitor, you replace with an open circuit. So if you look at the steady state equivalent circuit, there's a short circuit here, there's a short circuit here, there's the open here, and open here for the capacitors. So if I look at the current I1, there's no current flowing in here, so all that current is going to go around the loop. So you just add up all the resistors in that loop. So it'd be 50 divided by 2 plus 1 plus 7. That's a total of 10 ohms. So 50 divided by 10, it gives you 5 amps. That's the current I1, and the same as the current I2. For the voltage V2, that's simply equal to the voltage. There's no current flowing in here. Put a voltmeter here, it's going to measure the voltage across R5, which is 7 divided by multiplied by 5. It gives you 35 volts. The voltage V1, there's the 2 ways you can do it. You can take 50 and subtract the voltage drop across R1. The current I1 is 5, so 5 times 2 is 10. So if I put a voltmeter here, which is measured the voltage V open circuit of V1, then it'd be 50 minus 10 volts to give you 40 volts. Or I could have said that voltage V1 is equal to the voltage across R3 and R7. So you could have voltage divider rule. So it'll be 50 times R3 plus R5 divided by R3 plus R5 plus R1. Either way, you come out with a 40 volts. Energy is stored by the inductor. Again, inductance, just like the ideal capacitor, does not dissipate the electrical energy, if you assume it's ideal, but there's some small dissipation due to the resistance of the winding, of course. But ideal case, it will store that energy inside that magnetic field. So if you look at inductance as you in a storage cycle, the voltage across the inductor is as a maximum, but the current is going to start at a 0. So the current is going up, and the voltage is going down to 0. So the total energy, which is a product of those two instantaneously, initially it's going to be 0 because the current is 0. At a steady state, the voltage is 0. It's because short circuited, so the power would be 0. At this point, when they intersect, you give a maximum energy. So the shaded area, that's the energy, total energy stored inside that magnetic field. It turns out to be equal to 1/2 L the maximum current, when in this case with a steady state current, quantity squared. Let's get an example. It said to find the energy stored by the inductor in the circuit above when the current 2 is reached at a steady state condition, the final value. So draw the equivalent circuit at a steady state. This acts like a short circuit, so the total current would be 15. The maximum current would be 15 divided by 3 plus 2, and that gives you 3 amps. So the stored energy would be equal to 1/2 L I sub m quantity squared. 1/2 L in this case has to be in Henry, and current has to be in amp. So it's 1/2 6 times 10 to the minus 3, and the current is 3 amps, so it'll be 3 times 3 squared. That gives you 0.027 times 10 to the minus 3 joules, which is give you 27 millijoules. All right. One of the applications in this case would be a household dimmer switch, which is widely used. Inductance actually turns out to be widely used in all home electronics. Dimmer switch is a good example of it. The inductor in this case that is used in this figure, that here's the external. Either you have some kind of a turning knob to adjust the intensity of the light, or some of them you have a switch, and also you have a sliding switch that slides up and down to control the intensity of the light. Initially, when you turn off the lamp, the light bulb, the internal resistance is extremely small. Therefore, you have a very high current flowing. And then when the filament gets heated up, the resistance will increase, and the current will settle down. So the inductance can be actually used to protect the lamp or the rest of the equipment connected to the lamp from the rush current. That's one of the reasons why I use it. And the second reason they use inductance, we're going to see why you want to use a triac. Why not just use a potentiometer to adjust the voltage across the terminal of the lamp? It turns out that when you do that, a lot of the power will be dissipated inside that potentiometer, and then you're wasting the power. We'll look at that in a second. But the switching is happening, which is controlled by the rheostat. But every time the switching is happening with a triac, the SCR, there's some frequency is generated, high frequency. The inductance, as we said, it acts like an open circuit at high frequency because it is omega L. At a high frequency, is omega extremely large. So the reactant, which is the impedance of the inductance, will be extremely high, and therefore will block all the high frequencies noises coming in from the triac, from the switching circuits, the control switch right here. So those two applications. In addition to that, they use capacitor, which is hooked up from line to the neutral, connected in series with a lamp to avoid any spikes in the voltage to protect the equipment that's hooked up to it. So an inductance will control the rush current to protect the equipment, and the capacitor will can protect the equipment from a high voltage or spikes in the voltage. Now, if you look at the diagram here, the controllers for that to control the intensity of the light is directly connected in a series with a lamp. There are three applications. We'll look at the very low end, if you want the light to be at minimum intensity, or at the maximum intensity, or something in intermediate. The way the controllers actually is working, when you have a light, when you want to have the light to be extremely dim, then this part of the circuit, which is shown right here, the controller, the dimmer, it acts like a very low impedance. So it acts like a short circuit, so majority, all of the voltage from the line would directly appear across the lamp, which you see right here, and now you have maximum intensity. At the other extremes, the dimmer, or the controller, it acts like an extremely high impedance. And when it's extremely high impedance, then majority of the voltage is going to drop across the controller, the dimmer, and you have a very small voltage across the light, and then you have, which is shown right here, the blue indicates the voltage that appear across the lamp. The rest of it is appear across the impedance. Now, the intermediate of the impedance control the terminal voltage of the bulb. For example, if the controller network has a very high impedance, which is open circuited through the half of the cycle, in this case right here, so if the through half of the cycle the voltage is extremely high impedance, then the voltage across the lamp will be 0, and then the brightness will be less than the full voltage. This is non-linear relationship because of the power dissipation. Therefore, be a very small lagging as well due to the signal that's coming in later across the light bulb. Now, in this case, which is a 50%, then you change the states between open circuit and short circuit every 1/4 of a cycle. So this is 1/4 of a cycle. Every 1/4 of a cycle, it changes the states between open circuit and short circuit. And you look at the average, again, the power that we're looking at is shows up inside the light bulb is actually its average power. So you look at that average, is slightly less than 50%. If I look at the circuit diagram, here the control knob that controls the light intensity, in this case is right here, is connected to a rheostat and a branch pillar to the triac. Now, the setting of the rheostat, it determines the voltage across the capacitor reaches a sufficient high level to turn the diac on. So by adjusting this rheostat, it comes a time when the voltage across the capacitance, because if you're moving this voltage across this will be short circuit, the majority of voltage then will drop across to the capacitance. When that voltage is sufficient high enough to turn off this diac, the diac is just bidirectional diode, because remember the diode is only conduct in one direction. If you look at a sine wave, half of the cycle is positive, the next half of the cycle is negative. So you have to have a bidirectional to control the signal. So when the voltage is high enough, it will turn off the diac. The diac will develop a voltage right here at the gate of the triac. When that triac is turned on, then it will establish as a very low impedance, so it acts like a short circuit, and that would be the case right here. That establishes a short circuit, so a majority of the voltage then drop across the lamp. When the voltage is not, the voltage across the cap is not large enough such that the diac is off, it acts like a switch, and when the triac is off, then the voltage between the anode and cathode it acts like an open circuit, and the majority of the voltage, so when this is off, it acts like an open circuit. The bottom line is, when it's on, it acts like a short circuit. And the intermediate, then it determines when the voltage will be enough, such that it will turn on and off. Now, when this happens, then all the power, especially when at a high impedance, you have a very low intensity, it's almost down to zero, so you turn the knob all the way down, so you have a minimum intensity, but there's no power dissipated inside a dimmer switch. It's very small power because they're with a triac, and they have some kind of a heat sink to dissipate that, but you can actually show it in the picture right here. This right here is a heat sink for a triac to dissipate some little bit of energy to dissipate it when majority of the voltage is dropping across the triac, the control switch. But that's extremely low compared to the powers totals reaching the lamp. Well, again, the idea is to make sure the power that are reaching to the lamp is dissipated inside the lamp, and especially at the low end of it, and such that the power is not dissipated inside the control switch. Because somebody might ask, well, if all you're doing is trying to divide the voltage between this part of the circuit, the dimmer, and the lamp itself, why not just put a potentiometer in the rheostat and adjust it accordingly? As an example, let's say you have a 60 watt light bulb and you want to control with a dimmer switch, and if it's a 60 watts, it's 120 volts. So I can calculate the resistance of the lamp, which is V squared divided by P. P is equal to V squared divided by R. Is 120 volts divided by squared divided by 60 watts. That gives you 240 ohms. So if I set my potentiometer rheostat to 240 ohms, then you have 240 ohms here after the light has been turned on. Then you have 50% of the voltage drop here, 50% will drop here. Simple voltage divided to get 60 by 120 volts RMS. Again, that's not a peak value. It's RMS is effective value of it. So 60 volts over 60 volts over here. So the power inside the lamp now, which is dissipated, is this 15 watts, because 60 squared divided by 240, V squared divided by R is 15 watts. And the power that is dissipated inside the rheostat is also would be 15 watts. So the total is 30 watts, which is a 50%. But let's see what happens. Half of the power is dissipated inside the rheostat, and you're losing half of the power. There are two problems with that. Number one, you have a lot of heat dissipation. It's definitely as a fire hazard, and you need to put some kind of a huge heat sink in there to dissipate that energy. And if you had a 50 or 60 switches like that, then half of the power, especially if you put it in, well, if you put it down to zero, let's say you have a 10% intensity of the light, then 90% of it will be dissipated inside the rheostat, and you're losing all that energy. So that's the whole purpose of putting a controller switch in there, the dimmer switch, with a triac and a diac, and with a capacitor and inductance. Number one, to protect any spikes. Also, delete all the noise coming in from the trigger switch, and plus you're not dissipating energy inside a dimmer switch. All the energy will be in a lamp at a high and a low end of it. All right, that's one of the applications of that. But we'll stop here, and we'll have these posted for you. Thank you.